Welcome. This is podcast 3. If you've not watched the first 2 podcasts, watch those first. Then watch this one. All right? So this one continues on. So I'm going to start off with just recapping some of our rules. So indefinite integral formulas and properties. Right? So power rule, if we have x to any power except -1, the integral is just going to be to increase our exponent by 1 and divide by that same value. Divide by n plus 1, the exponent plus 1. Okay, so whatever you get when you add 1 to your exponent, that's what you're going to divide by, plus a constant. All of these will include a constant. The only time you're not going to use the power rule is if x is raised to the -1 power. Because if it's raised to the -1 power, or it's 1 over x, and what you see there for number 3 here, it is not the power rule at all, but its derivative, its integral is the natural log, and absolute value bars anytime there's any doubt that what you're taking the natural log of could be negative. So natural log of x with the absolute value bars. And even if it could only be positive, like x squared can only be positive, you can always just include the absolute value bars. You're never wrong. And then, of course, plus our constant. The easiest one of all, the integral of e to the x dx is e to the x plus c. It's its own integral and its own derivative. And then we also did one other that I went over, and that is if we have the integral of b to the x, some exponential, it's going to be, oops, don't forget the d to the x. Got to have our constant of integration there. What variable are we taking the integral with respect to? And so when we take the integral of bx dx, we're going to have b to the x divided by natural log of b. Okay? And that's because if we take the derivative of b to the x, take the derivative of any exponential, it's going to be, unless it's e to the x, it's going to be the same exponential again times the natural log of your base. So if there's no natural log of your base next to it, it must be that there was a natural log to your base below, so they canceled out. Constant multiple rule is number 4 there. You can move the constant multiple out. So any constant factor can be moved across the integral sign. It was the same with the limits, if you remember. Anytime you have a constant factor, you can just move that in front. But a variable factor cannot. Just a constant factor can be moved across. And then the 5th rule is that if we have the integral of a sum or difference, it's the same as the integral of each of those separate terms. Okay? Makes it a little easier. When you're taking the integral, simplify first. So when we were taking derivative, we had a product. We had 2 ways. We could use the product rule, or if the product wasn't too difficult, we could multiply first. You don't have 2 rules here. You don't have, and actually you have no way to deal with a product whatsoever. Okay? So when integrating, simplify first. Okay? So you can break up sums and differences. You can factor out multipliers. It often makes it easier just to get rid of it, not worry about it. Put it in front, and then just deal with what you have there. Makes it a little easier. Rewrite radical forms to exponential forms, and multiply and divide to change functions to sums and differences. Okay? You cannot deal with products and quotients. You can't undo products, and you can't undo quotients. So there is no undo to the quotient rule. There is no undo to the product rule. One thing you'll find out when we're integrating, you can take the derivative of many, many more functions than you can take the integral of. It is not quite as easy, and there's not always a method to go the other direction. So as much as possible, we want things simple. Okay? So we want sums and differences, no products, no quotients. Okay? All right, so here I'm just going to be applying some of those properties. I'm going to break things down as much as possible, make it nice and simple, and then we're just going to integrate. Okay? Here, there's just not much more to my function here than the 2. I'll leave that 2 in there because my d to the x, when I integrate d to the, actually, you know what, I will factor that out for a reason. Because sometimes you will just have the integral of dx. What do you do with the integral of dx? Well, the integral of d dx is x, right? Because the derivative of x is dx. So this one is 2x. It is a power rule. It's x to the, you could think about this as 2x to the 0 dx. Right? And so if we increase it by 1, we'd make that, oh, almost forgot, plus my constant. Don't forget that, plus my constant. If we have 2x to the 0 dx, and we're using our power rule, right, I could factor out that 2, and I'd have x to the 0 dx. And then my power rule, I would just increase it by 1. So I'd have 2x to the 0 plus 1 divided by 0 plus 1. Well, that's just going to be 2x plus c. Okay, so this really is just a power rule gone with a lot of more steps than you will ever use for a very, very simple power rule. I'm just going to kind of erase that. I don't think we need quite that much in there. I don't know, maybe I should have left it in there. But the derivative, or excuse me, the integral for dx would be x, because the derivative of x is dx. Okay. How about this one? All right, so we can pull out that 16, e to the t dt, and fortunately, the t and the dt match. The integral for e to the t is just e to the t plus our constant. So our integral here would be 16 e to the t plus c. And the integral of 3x to the 4th dx, we could pull out to the 3. So we have x to the 4th dx. Okay. Our integral, this is just going to be the power rule. So it would be 3 times x to the 4 plus 1 divided by 4 plus 1 plus c, and then we could simplify that. So that would be 3x to the 5th divided by 5 plus a constant. And remember, you can always take the derivative, right? So here, if I'm taking the, and so to check your work, so if I'm taking the derivative, for instance, of 3x to the 5th divided by 5. We know the derivative of the constant is going to be 0. Our 5 would move in front, our exponent would move in front, so we'd have 5 times 3/5 x to the 5 minus 1. Those 5s would cancel, and I'd have 3x to the 4th, which is what we started out with. So that's the nice thing. You can always check. Okay, let's do a few more. And these are, by the way, these are good ones to write down the steps to, all of these different ones that we're going to be doing together. I will recap at the very end of this lesson. I'll recap it with all of the rules. So every rule, power rule, trig functions, our exponential, our log. This is not, the list at the end of this lesson will not be all inclusive because we will be learning other techniques in other lessons. But it will give you a very good start to integrals. All right, so we want to take the integral of 2x to the 5th minus 3x squared plus 1. Okay. We can take the integral of 2x to the 5th dx. Notice I put dx there. I have to take the integral with respect to something. Minus 3x squared dx plus 1 dx. And now I could factor out my coefficients. I'm really not going to factor out the 1 though. So 2x to the 5th dx minus 3x squared dx plus, this is really just a dx. Okay. So x to the, all power rules, so this would be 2 times x to the 5 plus 1 divided by 5 plus 1 minus 3 to the x 2 plus 1 divided by 2 plus 1 plus x to the first divided by 1, right? Because this would be x to the 0 plus 1 plus our constant. And then we can simplify it. Yes, I've broken this down to more steps that you'll do when you're solving these out. But by doing this now, breaking this up into lots of steps, you'll understand the steps, and which is my goal. So this would be 2x to the 6 divided by 6 minus 3x cubed divided by 3 plus, well, that's just going to be an x. And now this reduces to x to the 6 divided by 3 minus x cubed plus x plus a constant. And if we take the derivative of our function here, and actually I should say that this is I should really write this as a function, just like we did when we took the derivative. The derivatives are functions, so are the integrals. We're getting back to the original function. And actually I'm going to do that. I'm going to go back and write that in there. I was kind of more focused on the rules. I almost forgot to tell you this is a function, and we need to write it as a function. So if we take the derivative of f of x here, the 6 would move in front. We'd have 6x to the 5th divided by 3. The 6 and 3 would cancel, so that would be 2x to the 5th, which is what we started with. We take the derivative of x cubed. That would be 3x squared, which is what we have. And then the derivative of x is 1. That's what we have up there. Okay? So back here where we were writing them, we should write this, our final answer here, as a function. So f of x equals, and let's see if can I move that over? Yes, I can. F of x equals, and let's move it over a little bit. F of x equals. And I think that was all we got up to. We only did that many examples. All right, here's our next one. Okay. So let's rewrite this. So we have the integral of, let's write that into separate ones. So we have 5 divided by x minus, oops, excuse me, dx minus 4e to the x. That's not a divided by dx. It's supposed to be a parentheses gone awry. So that's just the, in parentheses there, 5 over x minus 4e to the x with some squiggle next to my dx there. So I can split that difference into two integrals. I can also factor out the coefficients. So if I factor out the 5, what's left? 1 over x. Which you might not have realized what the integral was going to be until I rewrote it like that. Maybe you did, but maybe you didn't. I could factor out the 4. Okay, so now the derivative of 1 over x would be natural log of x. And then times 5, our function would be 5 natural log absolute value of x minus 4e to the x plus our constant. Okay? And that's our answer. Okay? So it might help you to recognize what the integral is when we factor out some of these constants like the 5 there. I don't think you had too much of an issue, would have too much of an issue figuring out that the integral of 4e to the x is going to be 4e to the x, but maybe 5 over x, it wasn't going to clear that it was going to be 5 natural log of x. Okay? This one will be a power rule. So I am going to rewrite this a little bit. So I've got 2x to the 2/3 dx minus the integral of 3x to the negative 4 dx, because 3 over x to the 4th is the same as 3x to the negative 4. All right, now so we'll take I could factor out those coefficients. So I've got 2 times the integral of x to the 2/3 minus 3 times the integral, oops, I forgot to put in my dx. Bad me. Dx minus 3 times the integral of x to the negative 4 dx. And now these are both power rules, and it doesn't matter that the exponent's a fraction, it's still a power rule. I'm just going to add 1 to it and divide by the same thing. All right, so I've got 2x to the 2/3 plus 3/3, and I have to divide by 2/3 plus 3/3, minus 3 to the 3x, minus 3x to the negative 4 plus 1, divided by negative 4 plus 1. So you notice that when you're using the power rule, whatever the exponent is going to be the exact same thing you divide by. Okay? Those two things are going to match. And then plus our constant. And this is a function, and we're going to clean this up a bit. So we've got 2x to the 5/3 divided by 5/3 minus 3x to the negative 3 divided by negative 3 plus c. Dividing by 5/3 is the same as multiplying by the reciprocal. So this would be 3/5. Oops. Let me just make that a little nicer. 3/5 times 2x to the 5/3. Now those negative 3 divided by negative 3 is going to now be a positive x to the negative 3 plus c. And so now let's just clean this up one last step. So we would have 6/5 x to the 5/3 plus 1 over x cubed plus c. And that's our antiderivative. And if we take the derivative of that function, we're going to get right back to the original. Okay? And so on any of these, if you're not sure and you want to, have me double check, show you in class and go over this one more time, or, just show you that, hey, that's correct and show us how you would check it, be happy to. Okay? Right, so different variable. So long as this variable and this variable match, we don't have any problems. All right? Doesn't matter whether it's an x, a u, a t, doesn't matter. So long as this variable, du, matches this variable, u, all is good. Okay? All is good. So this we could split up into 3e to the u du minus the integral of 7 over u du plus the integral of 2u squared du, and then minus the integral of 6 du. Okay? We could factor out the coefficients. So we have 3, it's our constant multiple there. So 3 integral e to the u du minus 7 integral 1 over u du plus 2 u squared du, and, well, I could factor out the 6 du. Integral of e to the u is going to be e to the u. So this will be 3, our function here. So, and actually I can't write f of x anymore. I can just put f of u, or just f equals 3e to the u minus 7 ln, absolute value of u, plus, now this one's going to be a power rule, 2u to the 2 plus 1 divided by 2 plus 1, and then minus 6, and that would increase by 1, 6u. because the derivative of du is going to, the integral of du is going to be u, and then don't forget your constant. And now we can just clean this up a little bit. There isn't too much to clean up. So our function is 3e to the u minus 7 natural log absolute value of u plus 2/3 u cubed minus 6u plus c. And there is the function. Oops. I was going to box it, but I'm going to have a problem. I don't have enough space. There's the function there. Maybe if I move this guy up just a little bit. There we go. In the box there, sort of box, that has 3e to the u minus 7 over u plus 2u squared minus 6 as its derivative. Okay, so there's the function, and there's its derivative, okay, where c can represent any constant at all. Okay, so a different variable doesn't matter so long as this variable of integration matches. So here we have 4 times the 5th root of w cubed dw. Okay, so different variable, but w and dw match. But you do want to rewrite as a rational exponent. Just like when we took the derivative, we rewrote any radicals as rational exponents. We do want to rewrite this as a rational exponent. Integral of 4 times w to the 3/5 dw. And we could factor out the 4 in front. And so 4 times the integral of w to the 3/5 dw. Okay. And now this is the power rule. Okay, so we're going to increase by the exponent by 1 and divide by that same value. So we have 4, we'll just call it f for function. Our function is 4 times w to the 3/5 plus 5/5 divided by 3/5 plus 5/5 plus c. There's only one term there. And now we'll just clean that up. So that would be 4w to the 8/5 divided by 8/5. And of course, dividing by 8/5 is the same as multiplying by 5/8. So actually, that's going to happen all the time. Anytime your exponent is going to be a fraction, you're going to be multiplying by the reciprocal. Because dividing by a fraction is the same as multiplying by its reciprocal. So we have 5/8 times 4w to the 8/5, which is just, so the 8 and 4 will cancel there. So that's just going to be 5 halves w 8/5 plus c. Okay. And if we take the derivative of that, just to check our work, so ddw of 5 halves w to the 8/5. The 8/5 would move in front, so we'd have 8/5 times 5 halves. And w, we reduce 8/5 by 1, so that would then be to the 3/5. And then this would reduce to 4w to the 3/5, which is exactly what we started off with. So there, just a little check of our work. Okay, so to check, you just take the derivative of your answer. Does it match? And if it does, you should feel pretty good. And let me see. I don't like these to get to be too long. I think I will just stop there, right here. And I'm going to pick up with this one, and I'm going to do just one more podcast, just solving out a couple more, okay? All right, so or maybe 2 podcasts. See you in the next podcast. Bye.